Hi, thanks for inviting me, Joan. I know this is after lunch, and I will try and keep it slow and simple, and hopefully interesting enough that you'll stay awake. So Calviri's mission, as Joan said, is to let's end cancer, and we think we've developed the technologies that will enable us to do that. But before I get into that, I wanted to tell you about this algorithm that we've developed that were the basis for making these technologies in the first place. I want to give you a couple examples of how this algorithm performs so that maybe you'll have some confidence that we could actually even accomplish this technology, this goal. The algorithm starts with this statement, which I fully agree with, by Newton. And the key word is simplicity. And I think Newton meant it in terms of physical processes, but I also believe that's true for biological processes, that there's our very simple solution to what apparently appeared to be complex things in biology. But there is a corollary for this. Doing simple is really hard. I promise you, it's really hard to do simple. It's very easy to do complex. And so in order to sort of enable this part of the equation a little more, we developed this algorithm that imaginatively we call simple. And the goal of the algorithm is to find a simple solution to what apparently appears to be a complex biological system or problem. And I want to show you some examples of that, how it can be applied. This is one, is how to make a plant or animal resistant to a disease. The conventional approach to this was to find a wild plant or animal that had a resistance gene, try to find that gene, and then transfer it into the agronomically important plant or animal. The problem with this is these organisms have 40,000 or more genes. The resistance is often multigenic. In fact, there has been no progress on this effort to do this. So we applied simple to this. And what it came up with is a very simple idea, surprisingly. Let's take the pathogen, which usually has 10 or 100 genes, take out one of the genes from the pathogen, make it defective, and then transfer it to the plant of interest. Then when the pathogen encounters this, it'll encounter a defective gene of itself, and it'll abort the infection. This works beautifully. It's very simple. I'm surprised nobody thought of this. Its first application was to save the papaya crop of Hawaii by making it disease resistant. That actually was the first GMO plant produced. It's now widely applied to vegetables and even in cheese production. It could have a lot more application, except, as you know, the greenies opposed GMOs, and so it's limited its application quite a bit. A second one, which I get a kick out of, is how do you get DNA into organelles, into chloroplasts or mitochondria? Chloroplasts and mitochondria have their own genomes, and everybody wanted to figure out how to manipulate them. So people devised very elegant molecular and genetic strategies to try and get DNA into these organelles. None of them worked. So John Sanford and I came up with a much simpler idea. Let's just invent a gun that shoots little tiny micro bullets, and we'll put DNA on the micro bullets, and we'll shoot them into the organelles. It worked the first time we did it. Worked fine. We transformed mitochondria and chloroplasts for the first time ever. It was the only time I had 2 science papers in one journal, and it was widely used since then. So these are just examples of how this algorithm can work, and we've applied it to many other things. That was the basis for developing using nucleic acids as vaccines. We developed that first. John and I invented that, and it was based on that algorithm. We'd invented degraders, therapeutics, which are in clinical trials now, cell targeting systems, systemic production of therapeutics and anti-infectives, expression library immunization, immunosignatures, and many more. If you're interested in them, I can tell you other applications that we've done with this algorithm. But let me tell you about the ones for cancer. So this is the focus of Calviri, is applied to this algorithm to cancer. I don't have to convince you it's a worthy cause. There's 20 million diagnoses, 10 million deaths each year, which many people don't realize. 75% of these are in developing countries. And with decades of research and funding, there's been, I will say, marginal and very disappointing progress against this disease. The ROI is very low. So one of the solutions that everybody agrees on, and there's a lot of work on, is let's get a highly sensitive diagnostic for stage 1 or earlier cancers. This won't end cancer, but it would effectively reduce cancer deaths, because for many cancers, even standard of care now is often curative if discovered at stage 1 or earlier. And as you know, there's a lot of companies in this space. Grail, others are trying to develop these nucleic acid-based diagnostics. All of them depend on detecting nucleic acids that are released from the tumor when they're very small. And it turns out they don't release much DNA. So the progress on these multi-cancer diagnostics has been slow. So we applied our algorithm, and it came up with a much an orthogonal approach to doing diagnostics completely. That is, why don't you take advantage of the fact that the immune system will see these tumors almost as soon as they start. Let's just measure the antibodies that are made to a tumor at the early stage. That's the easy side, the simple part. And then the problem then is, how do you detect those antibodies? Well, it turned out, if you follow the logic through, you can splay out all of the antibody binding diversity in an individual with 125,000 peptides on a surface. So you can make a diagnostic that can diagnose any cancer at stage 1 by simply putting a drop of blood on 125,000 peptides. It was very simple. I don't know why somebody didn't think of that. As of now, we're the only company that's developed a published papers on high sensitivity for stage 1 tumors, and we'll commercially have available this product for dogs in September. But really, we should go further than that. Let's really end cancer. To do that, the most practical approach would be to have a vaccine to prevent cancer. So applying that algorithm, the solution was to have a vaccine composed of shared frameshift neoantigens, which can't be from the DNA, we already know that, but it was obvious that you should be looking at the RNA for generating these neoantigens. And the RNA does misprocessing, creates these neoantigens, and sure enough, if you look at a tumor, it does a lot of RNA misprocessing. The antibodies respond to it, and so all you need to do is find those antibodies. This is where simple is really hard. We had to do that, we had to marry Intel to peptide synthesis so we could make chips with 2.2 million different peptides representing all the mistakes a tumor could make on each one of those chips. Once you do that, then it's a simple process to screen. That's worth about $60,000. It's a simple process to screen on these chips to find out which neoantigens each patient has in common with other patients and even other tumor types. And so we are confident now that we can produce a universal preventative vaccine for people that would largely reduce the incidence of cancer worldwide. So in conclusion, we think we can end cancer. I'd like to do that together with people to cooperate both clinically to help us with this and financially to support that effort. Glad to answer any questions. Thanks.
I have a question.
Sure.
So just for the record, since he's super smart and I'm not, so Stephen has been like on speed dial for me for the last 15 years. When there's a scientific concept I don't understand, I call Stephen. So thank you for that, Stephen.
All right.
But more importantly, here's my question.
That has to be a simple answer, though.
Hopefully. So one of the reasons that people have been leery about a diagnostic that can detect at stage 1 is for most solutions, we don't have something that treats at stage 1. Why are you different?
No, I agree that is a problem. And in fact, we literally went to a strategic. I hope no one else wanted to talk. We went to a strategic in the dog area and said, hey, we can detect cancer early in dogs, stage 1. Says, we don't want your product because we don't have any treatment for stage 1. So unless we have a treatment, we don't want the diagnostic, literally. And so I think that it'll be really interesting as these diagnostics are capable of detecting cancer earlier and earlier. It's going to drive a total transformation of cancer treatment. Any drug will have to have a safety profile that could be given to someone that's not sick at all. It'll be even better if it can be a systemic treatment that even when you can't find it by MRI or something, but you're confident it's there, you can treat it at such an early stage. If we ever really do get a diagnostic like that, I think it'll drive treatments that are completely different than what we do now.
Well, then hurry up and do it.
Yeah, okay. Thank you.
Dr. Stephen Johnston.